Well, I said in the last video we want to talk about concentration in this video, but before we discuss that, I just want to define a term very quickly, which is a precipitate. What is a precipitate? A precipitate is a solid that emerges from a liquid solution. And so what happens is you can have a liquid solution with an ionic compound in it, and that's dissolved in that solution. And if there are other ions present, then that ionic compound are so strongly attracted to those other ions, it will actually bond with those. It'll basically come out of the liquid and bond with the other ions, and all of a sudden with this liquid you will have this solid appear. And so this happens when you're like mixing two liquids together that have ions in each of the different liquids. But once you mix those two liquids together, now the ions are attracted to one another and they produce a solid. Okay, so I want to do example 9.1 to just kind of see an example where this could happen, and also practice doing your swap and drop with your the polyatomic ions that we learned about last chapter, and just make sure that we remember how to balance chemical equations. So this will be a good example for us to just play around with that and make sure that we don't forget those concepts, because they're still really, really important. All right, so example 9.1 tells us that we have this this situation where we're mixing together a solution of sodium carbonate and a solution of aluminum nitrate. And they tell us that when these two are mixed together, a precipitate forms. And so if aluminum carbonate is insoluble in water, what is the chemical equation for the reaction that happened? And so why did I put aluminum carbonate over here? Well, it's because they told us that when we mix sodium carbonate and aluminum nitrate together, they just offered up the information that aluminum carbonate is insoluble in water. If it's insoluble, something that's insoluble will not dissolve in water. So in other words, this aluminum carbonate is going to be a solid in our chemical equation, i.e., it is the precipitate that forms when you mix these two solutions together. Okay, so we're going to take sodium carbonate. We need to figure out the formula for that. We're going to add it to, we're going to combine it or react it with aluminum nitrate. We've got to figure out the formula for that. And it's going to produce aluminum carbonate. But aluminum carbonate doesn't account for everything that we have over here on this side, right? On this side over here, we have aluminum and we have carbonate, but what about this sodium and this nitrate? Well, that's going to be what the other substance is. That's why I have a question mark here, okay? So let's write down this chemical equation and see if we can both construct it and balance it. When we talk about sodium carbonate, we go to the periodic table and we see that sodium has is in column 1A, so it has a charge of 1 plus. Carbonate, we go to our table on page 245, and carbonate is, hopefully you guys have already memorized these at this point, but it's CO3 with a 2 negative charge, CO3 with a 2 negative charge. So we swap and drop those guys, and when we do, we get Na, and the 2 comes over here to the Na, and then we're left with CO3 that gets the 1 from the 1 plus up here on the Na, right? So swap and drop gives us that. So that's going to be our first substance, Na2CO3, right? Plus, and by the way, these are both solutions. They tell us that a solution of sodium carbonate, when you hear solution, this is going to be aqueous, is going to be our phase, because aqueous is, it just means it's something mixed with water, right? That is a solution. So this is aqueous. And the aluminum nitrate is going to be aqueous as well. So we can put that down there as our phase whenever we figure out what the formula is for that. But what does aluminum nitrate look like? Well, aluminum, when you go to the periodic table, it's Al. We're looking for Al, and we scan the periodic table. It is in column 3A. So aluminum is going to have a 3 plus charge, right? And then again, we're getting familiar with our polyatomic ions. Nitrate is NO3 minus. So NO3 minus. We swap and drop. The 1 from the 1 minus comes over here to the Al. So the Al won't have a number out next to it. The NO3 has got to get this 3 from the 3 plus that's on the aluminum. So when we swap and drop, we get a 3 out here. Now this 3 again comes from this 3 here, right? That's why we added a 3 to the outside of that. So we're combining sodium carbonate with aluminum nitrate, which we now have determined the formula to be AlNO3 with a 3 on the outside there. Again, this is also aqueous, all right? And it's going to produce aluminum carbonate. Now, what's the formula for, what's the formula for aluminum carbonate? We'll leave the Al3 plus here. That's aluminum carbonate. Go again to our periodic table. Actually, we just did that, right? It was CO3 2 minus. So not the periodic table, I'm sorry, our table on page 245. So CO3 2 minus. We swap and drop to get Al2, and then let me make that parentheses a little better. CO3 gets a 3 again. So we're going to have Al2 CO3 with a 3 next to it. And then last of all, what's left? Well, again, we use the aluminum, we use the carbonate. We got to figure out what the formula is for sodium nitrate because that's what's left over here, okay? So, and oh, by the way, I did forget to do this. This is our solid, right? So we're going to put a solid phase on that. And then finally, when we think about what the chemical formula would be for sodium nitrate, let me just write that name down here. Sodium nitrate. Sodium is in column 1A, so Na plus. Nitrate we saw was NO3 with a minus, just a 1 minus. So we swap and drop and we get NaNO3. So that's going to be the other substance here, NaNO3. And again, this one's just going to be aqueous. It's going to remain in that liquid form. It does not, they didn't tell us that it was insoluble in water, right? So it's going to stay dissolved in the water. All right, so there's our chemical equation, but we have to make sure that it's balanced, right? So the first job is to write the chemical equation down, but then we're going to have to add the numbers to make sure everything's balanced. Now, the easiest way to do this is don't think about your polyatomic ions as their individual parts, right? We're used to counting, each atom. So like for this first substance here, we notice that we have 2 NAs, we have 1 C, and we have 3 O's. And so we're used to thinking of those individually like that. But for our polyatomic ions, you don't want to do that. You want to think of this as 2 NAs, but then you want to think of it as having 1 carbonate polyatomic ion. And then over in the next substance right here, right, we've got 1 Al and we've got 3 NO3s. All right. Now looking on the other side over here, we check out our NAs, we've only got 1 of those guys. Our CO3s on the other side, we have 3 over there. For our ALs on this side, we have 2, and for our NO3s, we have 1. All right. So we can start with the Na, right? We need to get 2 NAs on the right side here. So let's put a big 2 in front there. And when I do that, I need to adjust my numbers, right? This Na now becomes a 2, but we also now have 2 NO3s. So let's change that to 2. And let's look at Al. For Al, we only have 1 Al on the left side here, and we've got 2 on the right side. So we're going to put a 2 in front of our Al here. And so that's going to change this number to 2. But not only is it going to affect the Al, it's also going to affect the NO3. So we have 2 ALs, but now we have 6 total NO3s, right? All right, so NAs look okay, ALs look okay. CO3s still need some work. For the CO3, we had 3 of those on the right side. We've only got 1 on the left side. So we're going to take this on the left side here. We're going to put a 3 in front of the Na. Now that's going to give us 6 NAs, but it is going to give us the 3 CO3s that we need, right? And so we're kind of going back and forth here. We notice now Al and CO3 is okay, but Na is no longer accurate. So we have 2 NAs on the right side here, and we want to make that, we want to have 6 of those guys. So we're going to change this to a 6, and whoops. When we do that, it's going to give us 18 NO3s. I feel like I'm getting out of control here. Let me make sure I'm heading in the right direction. Okay, we are heading in the right direction. We'll get there soon enough. So 6 NAs. Let's fix that. We have 6 of those. So now our NAs are balanced, but the NO3s are humongous, right? I was wrong. This is not a, I said it was 18. That's because I was taking this 6 and multiplying it by 3, but I'm not supposed to do that. I'm just saying we have 6 NO3s, right? So actually that's it. We're balanced now. We've got the same number of each of these substances on both sides. We have a balanced chemical equation, and that highlights what the precipitate was in this reaction. And again, the reason I know that it's the precipitate is because it's the solid that emerged whenever we combine together 2 liquids on the left side here. Okay, so that's how to think about precipitates. All right, the topic that I really wanted to make sure that we understood well was the topic of concentration in this section. It's because we're going to use concentration in future chapters as well. All right, so we're going to learn a pretty important formula as we consider concentration, but let me define it first. Concentration is the amount of a substance in a defined volume. And again, this is not a foreign word to us, right? We understand what concentration means. We know that, you know, if I mix in 1 packet of sugar into my tea and in 1 glass, and then I mix 2 packets of sugar in a tea in a second glass, then the sugar is more concentrated in the second glass. In other words, we've got the same volume of tea in both, but there's a greater amount of substance in the second glass than there was in the first, right? So the concentration is higher in that second glass. So that's the idea there. And so the reason it's so important that we understand something about concentration is because often the behavior of a chemical depends on its concentration, right? So if you go to the store and you buy some of these chemicals that you purchase, they are dissolved in water. And so you get it in liquid form, and on the back of the container, or sometimes on the front, it will tell you what the concentration of that liquid is, right? If you buy, I don't know, sulfuric acid, all right? It's not going to be pure sulfuric acid. It's probably going to be sulfuric acid that's been diluted. It's going to be mixed in with water, but there'll be a concentration on there to let you know, there'll be a number that represents the concentration to let you know how much sulfuric acid there is in there for the given amount of water. All right, so we're going to learn 2 units for concentration. And the first one is, I think, the more important of the 2, because this is the one that's going to kind of follow us throughout the future chapters. We're going to use this again. Maybe we'll use the other one. I don't know, but we'll definitely use this one again. So the first concentration unit we're going to talk about is molarity. All right, and we're going to use a capital letter M to represent molarity. And molarity is equal to, the formula we're going to use for that is moles of solute. All right, and we're going to use our normal abbreviation for mole, MOL, divided by the liters of solution. All right, not the liters of the solvent all by itself, but the liters of the entire solution after everything's mixed together. Okay, and we're going to use a capital L to represent liters here. So our shorthand form for this is M equals moles over capital L. All right, that's our shorthand formula for molarity. And you need to know that. You need to know that formula. You need to be able to use that formula. It's a simple formula mathematically, but you see that the unit for molarity is going to be moles per liter. All right. And so we can sometimes just use that capital M as our unit. Sometimes you'll see it represented that way. You won't see moles per liter. You'll just see a capital M, and you know that that means moles per liter. Okay, so let's do an example. That's going to be the best way to just understand how we start using this particular formula. And example 9.2 says we have a solution that's made by measuring out 150 grams of calcium nitrate. So we have 150 grams of calcium nitrate. And we're dissolving it in enough water to make 500 milliliters of solution. So what is that 500 milliliters? Well, that's a volume unit. So our volume is 500 milliliters of solution. All right. And they want to know, what is the concentration in moles per liter? Well, if they're asking for the concentration in moles per liter, that means they're asking us for the molarity, okay? So we're just going to, we need to plug our values into this formula here to figure out the molarity. But the problem is we need moles on top and we need liters on the bottom, and neither of these are moles or liters. We have grams and we have milliliters, right? So we're gonna have to do some unit conversions here. How do we figure out the number of moles that are in 150 grams of calcium nitrate? Well, we're going to have to use stoichiometry, right? We're going to have to use the molar mass, and we'll use the molar mass to convert this to the number of moles. But before we can use the molar mass, we have to know the chemical formula for calcium nitrate. So what is that? We're going to do swap and drop for that. We go to the periodic table, we look up Ca. Ca is in column 2. That means Ca is going to have a 2+ charge. We go to our table on page 245 because we're still memorizing nitrate. Nitrate's NO3-, and we write that down. And when we swap and drop, we get CaNO3 with parentheses around it and a 2, right? So that's our chemical formula for calcium nitrate. So we go to the periodic table and we see then that for calcium, which we have one of, calcium has a molar mass, an atomic mass of 40.08. So we write down 40.08. And we look at nitrogen. Nitrogen is over here in column 5A. It's got a molar mass of 14.01. Now notice, because of this 2 on the outside, we actually have 2 nitrogens. So we're going to take the 14.01 and multiply it times 2. And then we're going to add that to, we don't have 3 oxygens, right? We have 3 times 2 oxygens. So we have 6 oxygens. So 6 times 16 is the atomic mass of oxygen. We add all that up and we get a molar mass of, looks like 164.1. So I'm going to just write that down below here because we're running out of room. 164.1 grams per mole. So then to convert 150 grams to moles, we would say 150 grams of calcium nitrate. And just for space sake, I'm not going to write down calcium nitrate after the moles and after the grams. 164.1 grams, right? And when we do the math with that, we get, looks like 0.9141 moles. 0.9141 moles of calcium nitrate. Okay? Now, that's going to give us this unit up top here, right? That's going to give, so we can just plug that in, 0.9141 moles of calcium nitrate, divided by the liters of the solution. They gave us the amount of solution, not in liters, but in milliliters. So we got to convert that to liters. I don't normally write down this, but just to refresh your memory, we remember that there are 1,000 milliliters in 1 liter. And when we divide, divide 500 by 1,000, we get 0.5 liters, right? I would normally, once you get good at using the beauty of the metric system, is you can just move the decimal place to the left or to the right, depending on what conversion you need to do. And so I would just, knowing that there's 1,000 milliliters in a liter, if I want to convert to liters, I would just move my decimal place 3 places to the left of the 500 here and say 500 milliliters is equivalent to 0.5 liters, right? Which is exactly what we found down here. So that's what we're going to put on the bottom of our formula right here. So all we have to do now is just do the math with that. And when we do, we get that 1.8 0.28 moles per liter, because that's the unit that it asked us to use, is what the concentration would be of this calcium nitrate in this solution. Now again, if I'm looking at this though on packaging, usually it won't say moles per liter. It will replace that moles per liter unit with a capital M. So you'll see that, right? So we have the way you would read that is we have a 1.828 molar solution of calcium nitrate. Okay, let's do one more example. Example 9.3 will give us an opportunity to use this equation one more time just to make sure we're understanding that. So let me erase all of this. And our second problem may sound a little harder when we read it, but it's actually easier. It says the instructions for an experiment tell you to use 150 milliliters of strontium nitrate. So 150 milliliters of strontium nitrate. If I could spell, sorry, strontium nitrate. There we go. 150 milliliters of a strontium nitrate solution. So this is strontium nitrate that's been mixed in water, so it's going to have a particular concentration. And they tell us the concentration. If the concentration of the solution is 1.4, so the molarity equals 1.4 capital M for this particular solution. I don't like that M there. Let me fix that. I'll make that a little better. Sorry. All right, there we go. The molarity is 1.4 M. How many moles of strontium nitrate do you have? So they want to know how many moles do we have, right? Well, what is this 150 milliliters? That is the volume. So the volume of our solution is 150 milliliters. And we have volume in our molarity equation, the volume of the solution. It's just in liters. So again, if it's 150 milliliters, I know that I move my decimal place 3 places to the left, and so I know that's the same as 0.15 liters of strontium nitrate, right? Well, they've given me the molarity. I now have the volume in liters. I should be able to figure out the moles using this equation right here, right? Because I've got three variables in that equation, and I know 2 of them, so I should be able to figure out the third one. So what I'm going to do is I'm going to take this equation here. 1.5 liters. I just realized that I forgot to remove my equal sign there. And technically this would be 0.150 liters, right, to maintain significant figures. I'm going to rearrange the equation, this equation here, and I'm going to solve for moles. And so what would I do? I would just, a couple of ways you can think of that. You can think of it as cross multiplying. Or to get rid of the L on the right side, you can think of it as multiplying both sides by L. You'll get the same result either way. You'll get that moles are equal to the molarity times the number of liters. So we just got to plug in those values. The molarity is 1.4, right? And the liters are 0.15. Right? Since molarity is the same as moles per liter, in fact, let me write that down here. So instead of writing a capital M, I'm just going to remind you that that capital M means moles per liter, right? And so when we multiply that together, what happens? Our liters units cancel out, right? And we get a value of 0.25 moles, right? That turned out to be a super simple calculation. No stoichiometry required, we didn't have to look up go to the table in 245 to figure out the formula and the charge for a polyatomic ion. No swap and drop required, right? We just had to plug those values in. Super easy. All right. Well, cool. I hope that makes sense. The more you use this formula, the easier it's going to get. Don't forget it. You need to remember this formula because it is going to continue to be used in future chapters. Okay.